Okay, right, so we'll start, even though people aren't here, and to punish those for not being here, we're going to go through just quickly how to do the practical from last week. So there is a video of this already posted online, so you could have kind of looked at that if you could find it on Learn. So just super briefly, here's some maths of the first part of the practical, and all we're really asking you to do here is is explain how the fractionation factor, so that's this equation here, so that's the ratio of the absolute isotope ratios between two phases, how that fractionation factor relates to the actual measured isotope ratio between two samples. Because when we make measurements of isotopes in samples, we can very rarely measure the absolute value of the ratio of the two isotopes. We have to measure the ratio of those isotopes relative to that in some arbitrary standard. And that's this equation over here, like this. And actually for oxygen isotopes there are two standards, and we'll come on to that a little bit later on and explain how we convert between the two later on in the lecture today. But then you basically substitute this, well, you rearrange this equation here to make the subject of the equation the ratio of the sample, and then substitute that into the equation for the fractionation factor and rearrange it. And the important thing is this thing at the bottom. So this big delta down here, the difference between two samples when you're presenting the data in terms of these lowercase delta values, the difference between two samples is equal to 10 to the 3 log alpha. Okay, so that's something to remember, because that's important. And then we need to think about what are the assumptions. So in an exam kind of question setting, there may well be, I guess we refer to it as a plug and chug type thing, where you get some numbers and you plug them into some equation, and you chug through the calculations and you get a number at the end, and you go, oh, aren't I clever, I got a number at the end. But really what we're looking for is some evidence of understanding about the underlying science behind that kind of plug and chug operation. So we're talking about, in this case, some of the assumptions that are used when we use isotopes to measure paleotemperatures. So these are things like, are the two phases that the isotopes are fractionating between, are those in isotopic equilibrium? And we'll talk about that in more detail today. In the case of oxygen isotopes, we quite often assume that we know what the isotope composition of the water is, because we don't have that preserved. Okay, we only have the carbonate. We might have things about assumptions about there being no diagenesis, so there's been no re-equilibration of the isotopes since the mineral was first formed. Things like that are what we're looking for in this kind of part of the practical. And similarly, we might ask you to explain some of the underlying thermodynamics or some of the underlying physics of why these isotopes, or in the case of magnesium and calcium, the element ratios, might respond to temperature. Okay, so some description kind of based on, I guess in this case, we're looking at the competition between the enthalpy of fitting of the preferential having the heavy isotopes and the heavy bonds, and the lighter isotopes and the lighter bonds, versus the entropy term that you want all of the isotopes to be evenly distributed across all phases. So that's the underlying reason for there being a temperature dependence on the fractionation factor. Okay, and you could go through some of the equations of that to illustrate your answer. Similarly for the magnesium calcium, the underlying physics is that there's some battle between enthalpy and entropy. Okay, so that it costs some kind of energy to fit magnesium into the calcite lattice structure. So this is a model of the calcite lattice structure which I found at the back of the lab. And if you have a different cation in the see-through site here, then that will basically distort the lattice, which costs some energy. Okay, and then that is kind of counteracted by the energy that you kind of get back, as it were, from distributing your elements evenly across all phases. So actually going into the plug and chug type of part of the practical, where we're going to need to extract some numbers from the graphs and plug them through some equations to get some answers. So we've got this sediment core, which has got a record of oxygen isotopes measured in carbonate and magnesium-calcium ratio also measured in carbonate. So the first part, you have to basically choose, reading off the graph, a value to represent the Holocene. Okay, so I've picked basically -1 as the oxygen isotope value, and I think 3 and a bit for the magnesium-calcium. And then choose where the LGM is, and you should know where the LGM is, and pick a value. I've picked 1, and I think I picked 3. There we go. So you might want to think for later on about how precise those determinations were. You need to convert the oxygen isotopes, which were measured against the carbonate standard, which was the PD belemnite, to as if they were measured relative to the water standard, which is called standard mean ocean water, although it's not actually necessarily the exact mean of all the ocean. It's just a pot of water that sits in Vienna that someone has decided that is approximately the average of the oceans. So there's this equation that relates those two, and we'll come on to why this equation has this form and why it's not just a constant factor offset between the two. So we now have the isotope basically ratio expressed in this per mil notation for the carbonate relative to a water standard. The next step is to work out the temperature. Okay, and we use the magnesium-calcium ratio for that temperature. So that's basically just taking our magnesium-calcium value that we read off the graph, plugging it into this equation up here at the top, and then rearranging it. So divide by 0.52 both sides, take the natural log of both sides, and then divide by 0.1. So that's what's that gives us the temperature. Now that gives us the temperature in degrees C. To get it in Kelvin, we can kind of add the 273.15, which is something you should know. So that gives us the temperature. Now the next step in the practical is to actually work out, instead of using the oxygen isotope paleotemperature equation, which is this thing up here. See, I'll give myself the pointer. That'll be fun, won't it? Pointer options, the pointer. Okay. Does that make it slightly easier to see the pointer? Nah, maybe not. So instead of using that equation to work out temperature, we know temperature. We're using it to then work out the fractionation factor. Okay. And if we know the fractionation factor, we can then calculate 10 to the 3 log the fractionation factor. And we'll know from the first part that is equal to the difference between the isotope composition of the two phases expressed in the per mil notation. So we're then able to work out what the isotope composition of the water is, okay, just by simply plugging this into this equation and then rearranging it to get the isotopic composition of the water. So that's what we do for the last step down here. And we can see that in the Holocene, the isotopic composition of the water is minus 0.56. So that's different to the standard mean ocean. Okay, so the standard mean ocean should be 0 by definition. But it's not, and that's because there are spatial variability. There is spatial variability in the oxygen isotope composition of the water in the surface ocean, and that's because the oxygen isotopes should correlate with salinity, and you should think about why that is. And we get a value for the LGM of that's a lot more positive in terms of its delta value, so it's got heavier. The ocean has got heavier isotopes than in the Holocene. So I guess the last part of this practical is basically asking you to explain why that is. Okay, and we went through a little bit of this last time in terms of when we evaporate water, that preferentially removes the light isotopes, and then as that water then rains out, the clouds or the atmosphere then loses heavy isotopes as the water condenses, leaving the remaining atmosphere progressively enriched in the lighter isotopes. So when eventually that forms precipitation into an ice sheet, we've removed light isotopes from the ocean. Okay? And that fractionation can be quite large due to that Rayleigh distillation effect, which you should know about. So this means that when we grow a large ice sheet, we're removing lots and lots of light isotopes. So the remaining ocean, so this is basically a proxy measurement for the ocean isotopic composition. You can see during the glacials, we have higher delta 18O than during the interglacials. So just to point out here that it's quite often for paleoceanographers to switch the vertical axes of their graphs around just to annoy you. And they do this because paleoceanographers are not the brightest bunch of kids in the world, and they quite often like to think of as up being warm and down being cold. Okay, so in terms of oxygen isotopes, more positive tends to be more ice, so a colder kind of climate conditions. I guess there was a last part of the practicals on this. So the last part was basically to try and think about some of the assumptions and errors that go into paleotemperature calculations. So one of the things we quite often find is that in a paleoclimate record we might not have that independent measure of past temperature. We might only have the oxygen isotopes. So those can be affected by two things. So you've basically got oxygen isotopes preserved in carbonates, and there's a temperature-dependent fractionation between the water and the carbonate. But there's also a kind of a global climatic signal that controls the isotopic composition of the water as we grow and melt ice sheets. So what we're asking you to do here is think about what kind of answer would we have got if we just assumed that we just had oxygen isotopes and we assumed that the isotopic composition of the water was the same as it was when at the LGM and the Holocene. So imagine we only had the measurement of the Holocene and the measurement of the LGM. We could kind of work out what the isotopic composition was of the water in the Holocene, because we know the temperature because it's now. We could work out the isotopic composition of the water, or we could have measured the water and found it to be minus 0.56. And then we would have had our measurement of the carbonate, which would have been this. And if we'd have plugged that into our paleotemperature equation for oxygen isotopes up here, you should have got an answer of about either 10 or 11 degrees, depending on how you do your rounding, Celsius. So you can see that that is very different to the actual paleotemperature measured by magnesium-calcium ratios. So we've basically, by ignoring the effect of the ice volume changing and changing the isotopic composition of the water, we've estimated a paleotemperature that's much colder. So you can think of oxygen isotopes as a combination of ice volume and temperature change, and both of them kind of work in the same direction. So more ice on the land means heavier isotopes in the ocean. Heavier isotopes recorded in your carbonate is an indicator of colder conditions. So they both act in, if it's cold, you'll get heavier isotopes in the carbonate. If it's got lots and lots of ice on land, then you'll get heavier isotopes in the water, which will then mean you'll get heavier isotopes in your carbonate. So they both work in the same direction. And also you need to think about the accuracy and precision of your results. Now if you see in an exam accuracy and precision, that means two very separate things. Okay? So precision is basically the size of the error bar on your number. You should get very, very kind of like, if you've got lots and lots of significant digits after here, you might say that it's a very precise number. The accuracy is you getting the right number at all. So things like how accurately you can read off this graph here, that might affect your precision. Some of the constants in some of the paleotemperature equations, so they might also determine the precision. So you can see that this is basically a calibration line through some data, and we'll come on to in calibrations in the lecture today. But you can see there's quite a lot of spread of data around like the theoretical kind of best fit line. So that means that we don't actually know these constants that well. So that means that feeds into some uncertainty into our final answer. So that affects the precision. Accuracy might be not knowing the isotopic composition of the water exactly, or making an assumption about isotopic equilibrium, or making an assumption about there's been no diagenesis. So accuracy are things that give you totally the wrong number. Precision are things that give you kind of the right number, but with some larger uncertainty about it. So those are two separate things that you need to think about separately when asked in exams. Okay, so I think everyone who's going to turn up has turned up. So we're going to start the second stable isotope lecture on stable isotopes. So I guess to forewarn you, there will be quite a lot of maths in this today. Don't worry if you don't follow through all of the steps in the maths. The important things is understanding where the start point of a kind of a mathematical shenanigans comes from, and that it can therefore lead to an end point that kind of means something. Okay. So, there you go. I was wrong. Someone did turn up late. There we go. So I guess I've been talking about this term isotopic equilibrium, and this is where kind of you have maybe some different chemical species, and the element that you're interested in this case maybe oxygen, the isotopes of that can exchange quite readily between the different chemical species. So the example here is CO2 and water, and because there's a chemical reaction between CO2 and water, if you have those two species basically in contact with each other, the bonds of these molecules will constantly be being broken and remade as this equilibrium moves backwards, as this chemical equilibrium moves back and forwards. So it's very easy to exchange your isotopes between the different phases. So that means that it's very easy to achieve the isotopic equilibrium where the proportion of the different isotopes in the different phases is really just due to the temperature and the preference for the heavier isotopes to be in the heavy bonds, the stronger bonds, and the lighter isotopes to be preferentially in the lighter bonds. Weaker bonds. Oh my God. Sorry, it's early for me too. But the problem with I guess most of the isotope geochemistry done for geosciences is that the things that we measure are solids, because solids tend to survive very well in the geological record. So this is a little picture of a calcite rhomb, and you've also got some other things that are made of calcite that we might want to measure the isotopes in here. And the thing is, once an oxygen atom is in the middle of that crystal lattice, it's very hard for it to get out. Okay? It's really stuck inside the crystal lattice. Very, 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 very hard for it, especially at low temperatures. So how is it at all possible that we could ever get isotopic equilibrium between a solid and another solid? Two minerals, maybe? Or even just a solid and a liquid? And it's more complex than that even. So quite a lot of the things that we will measure will be some biologically mediated carbonate production. So either a mollusk or we've got an echinoderm here, or a foram down at the bottom. And basically these take ions from solution in seawater or in river water or in whatever, some kind of fluid that they're living in. And they pass it through. They pass those ions, those calcium ions, those carbonate ions. They pass them through a cell. Okay, some kind of, at least one cell, part of their body. Sometimes they precipitate the carbonate within the cell. Sometimes they precipitate it outside of the cell, like just on the surface of it. And sometimes there's a kind of a more complex kind of precipitation in the region around it that's due to the organism modifying its kind of surrounding chemistry. So if we want to be in isotopic equilibrium with the water, the atoms have to be able to exchange between the carbonate over here and the water over here. This is impossible. There's no way that they're going to be able to do that. Through all of the diffusion and chemical reactions that go on inside of a cell, it just ain't happening. Okay? So isotopic equilibrium never occurs in its truest, most literal sense between kind of water and the carbonate when the precipitation is biologically mediated. So that never happens. So this is just a close-up of that. Okay, there's no way that, so you can get an equilibrium between the water here and here, so the oxygen here and here, here and here. Oh, that's not an oxygen. The oxygens are red. But getting it through all of this stuff in the cell, it's just not happening. But all is not lost. Okay, even though it's not truly in isotopic equilibrium, what we can do is we can just do what we would call an empirical calibration. So we just measure a whole bunch of different samples that grew in a range of known settings, and this can be sampled in the natural environment or in the lab. So we could get a bunch of forams or corals or mollusks or whatever organism we're interested in measuring the shell of. We could grow them in some fish tanks, and this is being done in the department in the Grant Institute. We could grow them in different fish tanks of different temperatures, and then measure the isotope difference between the water and the carbonate. And that's what this graph is showing here. So these are some examples for foraminifera, and you can see that for different species, there's a very kind of robust linear relationship between the temperature and the isotope difference between the water and the carbonate that they're producing. So we could do that over a wider range of temperatures, and we seem to get a slight curve on a relationship, which does kind of make sense in terms of we should be getting this 1/T relationship from the thermodynamics. But quite often you'll see that the calibration line that people do or use is actually a quadratic. Okay, and you should remember from Earth Modelling Prediction 2 that you can approximate any function over a narrow enough range of temperatures with a quadratic or with a polynomial. Okay, so we're effectively just using a polynomial because it's easier to do the linear regression using a polynomial than using kind of some weird logarithmic thing. So rather than use the kind of theoretical fractionation factor and this robust thermodynamic argument, when we work out paleotemperatures with isotopes, what we're quite often doing is just measuring some stuff, either going out into the field and sampling organisms that grew at different temperatures or growing them in the lab, coming up with a calibration curve that's between the isotopes in the sample and the isotopes in the fluid that they're growing in, and just using that empirical calibration. Okay? And that empirical calibration, as you can see here, can be different for different species. So the difference between these different lines is sometimes referred to as a vital effect, which is basically just a species-specific additional fractionation that we don't really understand, that is due to this kind of any isotope fractionation that occurs between isotopes being in equilibrium between CO2 and water and bicarbonate ultimately in the water, and getting to the carbonate over here. So we don't understand this bit very well at all, but we can just calibrate for it, which is what we do there. Now, at high temperature, in high temperature systems, we can do the same thing. We can do experiments in the lab at high temperature, and we can grow minerals and measure the differences between them, and that's effectively how these things arise. But we've also got the problem that these are two solid phases that we're trying to equilibrate isotopes between. So the example maths here, doesn't really matter also, but just as an example, we could be using quartz and magnetite. We could measure the oxygen isotopes between those two. Okay, so that gives us a difference of 4 per mil. So that's this delta value here. We know that's equal to 10 to the 3 log alpha. So we know that 4 is that number there, and that must equal this. We can rearrange that to give us temperature. So that's the ideal case, but how does that exchange actually happen? Because those are two solid kind of minerals, so you can't exchange the isotopes between them. So the idea here is that actually the equilibrium is not actually between the two minerals. So this is an example between olivine and quartz. So the isotopes are not exchanging between the two minerals. They're exchanging between the mineral and some fluid that mineral is crystallizing out of. Okay, and because those are two minerals that actually crystallize out at the same time. So for high temperature oxygen isotopes or high temperature isotope thermometry, not only do we have to think about the isotopes in equilibrium, but it's not, more specifically we need to think about, did those two minerals crystallize at the same time? Because if they're crystallizing at the same time, then the elements can proportion from the fluid into the different crystals as if they were in equilibrium and able to exchange. So you could think of it as basically as atoms are being added to the surface of these minerals as they grow, here and here, then there could potentially be an exchange of isotopes from the surface into the fluid and backwards and forwards. Okay? That means that you can effectively be exchanging between the two minerals. And this is possible for some systems. So for instance, this is an example of plagioclase and olivine. So this obviously couldn't have been quartz and olivine because those minerals do not crystallize out together ever, which is something you should know, especially if you're on the geology degree program. But you should remember from a kind of a ternary diagram like this, as you start to precipitate out from a magma, say, of a composition of A, okay, you remove olivine until you get down to this cotectic line, where as you're on that cotectic line and you move down towards the eutectic, you're precipitating out, or you're crystallizing both anorthite and forsterite. So it's quite common in systems that you're able to actually precipitate out two minerals at the same time. So, but you need some understanding of which minerals in your rock would have been doing that. The last kind of thing I want to mention about these high temperature isotope paleotemperatures is this idea of diffusion within the actual solid crystals once they've formed. And I think you might cover this with Jeff in a future lecture. But the idea is that even though crystals are solid, and it's very hard to get an atom from the middle of it to the edge of it and out into another crystal, geological time is very long. Okay, over very long time periods, it is possible to diffuse isotopes between solid phases. So this is what this graph down here shows, and it's kind of quite complicated, and there's far too much on it, and I apologise for that. But basically, we've got temperature along the bottom and the top axis, going from kind of cold to hot, and then you've got diffusion in this kind of slightly strange unit of centimetres squared per second on the vertical axis. So this is fast diffusion and slow diffusion. But look at the numbers here; they are like 10 to the minus 20. 10 to the minus 10. So these are, whatever units they're in, 10 to the minus 20 of something is always going to be a very small number. Okay? So what this means is as things get hotter and hotter and hotter, an individual mineral, diffusion will happen faster and faster and faster in it. Now, if that diffusion is fast enough for the element to basically move from the atom to move from the middle of the mineral to the edge of the mineral, on the time scale since it's crystallized, then it means that the isotopes can exchange between minerals. So the relevance for this is that, move on here, is that if the diffusion is fast enough, once the crystal has formed, then if you measure the isotopes in 2 different mineral phases and work out the paleo temperature from that, that won't tell you the temperature that it crystallized at. That'll just tell you the temperature at which the isotopes were able to exchange at. So it's basically just telling you a cooling temperature for that mineral, which is kind of useless because that will be the same for every mineral. So you can only use paleothermometry in high temperature systems on minerals that have very slow diffusion. Okay, so things like quartz, olivine, if it's dry. Okay, those are good minerals for measuring paleo temperature because they tend to have very, very slow diffusion even at high temperatures. Okay, and this concept, and Jeff will go over this in more detail with geochronology, is also kind of very important. In that at very high temperatures, so for instance, if you look at maybe the potassium, have we got potassium argon here? We've got argon, so that's kind of like basically potassium argon dating. At very, very high temperatures, you might form a mineral, a biotite or a feldspar, but if the mineral stays very hot after it's formed, then the argon that's being produced by radioactive decay will just diffuse out of the mineral. So if you then dated it, it would have an age of 0. It's only once it's cooled down enough that the diffusion of either the parent isotope or the daughter isotope are basically locked within the crystal. That's what temperature it gives you. So with almost all radiometric dating systems, what these are telling you is not the time at which a particular mineral formed, it's the time in which a particular mineral cooled to a temperature low enough that it couldn't kind of diffuse out of its mineral. Okay, so that part of the lecture was just kind of covering this concept of isotopic equilibrium, which is really important that you have a good grasp of what it actually means and why it's important. Okay, so the rest of the lecture, we're going to be talking about an example of the use of isotopes in paleooceanography. The particular example is boron isotopes, and this is actually not a proxy for temperature. We quite often use boron isotopes as a proxy for the pH or the acidity of the environment in which this thing was formed. Okay, so this is the bit where there's going to be quite a lot of maths, but if you get stuck with the maths, don't worry too much. I mean, I've made this PowerPoint so it's got all of the steps in it, kind of one by one. So I think it's already posted on the Learn site, so you can go through it in your own kind of speed later on, as it were. And you can also post questions to the discussion forum if you want to. That would be fun. But just to summarise what's going on here with boron. So boron has 2 isotopes. Well, it has many isotopes. It has 2 stable isotopes, boron 10 and boron 11. One with 5, one with 6 neutrons. And it also has this quite interesting chemistry. It's not that interesting. It has a chemistry where in the ocean, boron has 2 main chemical species which it has. One is boric acid, the other is the borate ion, and they kind of react backwards and forwards with water. So basically boric acid reacts with water to form this hydrogen ion, and borate ion, which is why it's an acid. So there are these 2 different species that have boron in them, which means that because the bonding environment of boron in boric acid and borate are slightly different, that means there must be some isotope fractionation between the 2 species. And if we look at this equation up here, because it's got a hydrogen ion on it, okay, there must be some pH dependence on the equilibrium point of this chemical reaction. And this is quite useful because knowing something about pH in the past would be quite nice, because pH is quite an important parameter of the carbon cycle. So this is a map of how the pH of the ocean has changed since we've started pumping loads of CO2 in the atmosphere, which we can measure now with a pH meter if you just wander around and dip it in the ocean. But we can't do that in the past. So if we want to investigate some of these potential carbon cycle changes of either maybe changing ocean productivity or changing how much CO2 has been put in the atmosphere by volcanism or maybe sudden gas hydrate release, all of these different carbon cycle perturbations might have slightly different effects on ocean pH. So if we had a proxy for that, we'd be able to somehow know a little bit better about the carbon cycle in the past. So I kind of said pH is important for the carbon cycle. This is also stuff you should know. So this is the carbon dioxide concentration in the atmosphere has changed a lot in the past. So if we knew more about the carbon cycle, we might be able to explain some of these changes. And boron isotopes are hopefully going to help us do this. So this is the two species. This is boric acid. This is the borate iron. And because the boron in the middle is bound differently between those two species, and it's actually the bonding is quite covalent, we have quite a large isotopic fractionation. So that's almost a 3% difference in the isotope composition between boric acid and the borate iron. Okay? So this suggests that actually, although the borate iron here has got 4 bonds relative to the 3 in the boric acid, the boron is more strongly bound in this than this. Okay? Because you can see, because it's got the heavier isotopes in it. So let's go a step back into the chemistry of these things now. So I mentioned that the relative proportions of boric acid and the borate iron will be dependent on pH. Okay, that's because this equilibrium reaction here has a hydrogen ion in it. So the equilibrium constant of this will have the concentration of the borate iron, the boric acid, but also hydrogen ion. So that means if you look at a range of different pHs, at low pH we've got more boric acid, and at high pH we'll have more borate iron. So the effect this has on the isotopes is quite important. Well, it's quite profound. Not profound. It's not profound. It's just isotope geochemistry. So it's important for using it as a proxy for pH. So if you imagine that the bulk ocean would have if we had measured all of the boron in all of the ocean, it would have a value. Right? Let's say that value is somewhere around 40 per mil positive. So if we could measure if we could get all of the boric acid and all the borate iron anywhere in the ocean, we kind of added those together and we measured the boric acid composition of that would be this value. Now, very low pH, almost all of the boron is in boric acid. So the boric acid must then have, if all of the boron is in that form, it must have the composition of the bulk ocean. Whereas if it were all as the other species, if it was all as the borate iron, then the borate iron would have the same composition as the bulk ocean. But if you had some mixture of the two, okay, so you had some mixture of the two over here, then to maintain the bulk ocean having the bulk ocean isotopic composition, because we're not taking any isotopes out of the ocean, okay, it's all staying within the ocean, it's just partitioning between these two species, then some of it must be heavier than the average and some of it must be lighter than the average. Okay, so we can actually do the maths if we were so inclined, and all this is saying is that the total concentration of boron times the isotopic composition of the total is equal to the sum of the individual parts, so equal to the sum of the concentration or the amount of boric acid times the isotope ratio of the boric acid plus the amount of borate iron times the amount, of the isotope ratio of that. So we can do some rearranging here, because we know that the fractionation factor is just going to be the ratio of this term divided by this term. Okay, so we can re-express this. We call this a mass balance equation, because it's just balancing the masses of all of the isotopes so they add up to the total. So we can basically rearrange this to express this, okay, in terms of just one of the species. So we basically remove the boric acid term out in this case. So that is equal to this, which is what I've done there. You can kind of simplify that some more, kind of try and factorise out, what are we factorising out here? The isotopic composition of borate ion is equal to that. And then we can rearrange that to get basically the equation for the composition of one of the species, in this case borate ion, okay, as a function of the relative proportions of the two species and the total isotopic composition and the fractionation factor. So this basically allows us to work out the shape of this graph here. So that was expressed in terms of the absolute isotope ratio. We can't measure the absolute isotope ratio, so we need to convert it, all of our isotope ratios, to the delta per mil notation, which is this. We can rearrange that to get this equation here, so we can then substitute in the ratio in the sample into this equation up here, and that's what we get down here. It's just plugging kind of one equation into another. Now that gives us an equation that's got the isotopic composition of the standard in, which is kind of irrelevant. So and they also will cancel out. Okay, we'll just divide through by the isotopic composition of the standard, and that goes away. We actually want to isolate the equation, so we just have the delta value of the borate ion, so we need to -1 and times by 1,000. That's what we're doing in these steps here. And this then gives us the equation for the measurable isotope ratio in terms of delta 11b of the borate ion, kind of as a function of the relative proportions of the species and the isotopic composition of the total and the fractionation factor. Okay, so we can do some more manipulations of this to make it kind of slightly more palatable for those that love maths, and I'm not going to go through every step on here. But basically, what we're doing now is just rearranging the equation to try and get this term along the bottom. Move along here. So all I've done is rearrange that multiple kind of different ways. You can go through it in your own time. But we've now got an equation, the isotope composition here, of the thing that we can measure, the total isotopic composition of the whole ocean. We've got this alpha -1 times 10 to the 3. Okay. Now, what does that mean? Alpha -1 times 10 to the 3. Now, if we go back to the previous lecture, we've got the fractionation factor. We can rearrange that by expressing it in terms of the per mil notation. Okay, so we plug in our per mil notation things up here. Now, imagine if one of the phases that we're looking between, so, is actually got an isotopic composition that is the same as the arbitrary standard. Okay, that means that it would have a delta value of 0. Okay, so imagine if you were looking at, instead of looking at the fractionation factor between two phases, the fractionation factor between one phase and the arbitrary standard that you're measuring. So that's what you would get here. That value would become 0. Okay, so you would then effectively have this equation here. So what we're looking at now is it's effectively a way of expressing the fractionation factor. Instead of expressing it as a fractionation factor as the fractionation between two phases in terms of their absolute isotope ratios, it's a way of expressing that as the difference in isotopes expressed in this per mil notation between two phases. Okay, so this is basically this term epsilon. So it's the fractionation between two phases expressed in terms of their their fractionation factor. Now, yeah, so that's what this says. I wasn't expecting that. Yeah, here we go. So if we think about what if we're just thinking about two different things, both of which are different standards for the same thing. So in this case, think about we've got, for the example of oxygen isotopes, we've got two standards. One of them is the PDB standard for measuring in carbonates. One is the SMO standard for measuring it in water or in gases. And there's a fractionation between those two standards, okay, in terms of the actual the isotopes between them. So if we want to convert between the two, we can use this equation that we've just worked out for the difference in isotope ratio between two things based only on their fractionation factor, but expressed in terms of the per mil value. So that's what this shows. All we're doing here is rearranging this equation for alpha, okay, which we derived last week. Rearranging it, okay, and that gives us the delta value of one phase, delta value of another phase, or in this case one standard and the other standard, expressed just as the fractionation factor and the fractionation factor expressed in this per mil notation. So this is where this equation here ultimately comes from. Okay, so this basically explains why, when we convert between SMO and PDB in terms of our standards, we don't just use the difference in delta value between them. We also need this kind of alpha term in there as well. So briefly back to boron. So this is basically just where this epsilon has now appeared from. It's basically just replacing this alpha minus 1 times 10 to the 3 in there. So this gives us this equation, which allows us to work out the delta 11B of the borate ion as a function of the fractionation factor expressed as a per mil notation, and the relative proportions of these different species. So we need now to think about how we can incorporate the pH dependency of these different species. Okay? So this is, I guess we've already kind of touched on this before, but basically this is the equation that is the speciation between borate ion and boric acid. Okay, that goes backwards and forwards to this. Produces a hydrogen ion, so it should be pH dependent. We can express the equilibrium constant of that reaction like this, so products over reactants. We can basically write out that this equation here is the boric acid plus the borate ion equals the borate ion plus, this is now just this equation here rearranged to give the boric acid concentration. So move that up to there, that down to there, that gives this. So this is now basically an equation that gives us this amount. So all this equation is saying that plus that equals that plus that, which is basically saying it's the same thing. So we can, which is basically the total boron, which is all that is saying. And then I can rearrange that, basically factor out the borate ion to give me this equation here. And then I can rearrange that to give me the concentration of the borate ion as a function of the total concentration and the ratio of the hydrogen ion concentration to the equilibrium constant, which is there. Now this next kind of bit of mathematical trickery here is just related to the power of logarithms or the rules of logarithms. So if you have, because pH is minus log to the base 10 of the hydrogen ion concentration, and pKb is the same but for the equilibrium constant. And if you've got basically one thing divided by another thing, that's the same as the difference between two logarithms. Okay, so if you minus 2 logs, that's the same as 1 over the other, which gives us this. So this now gives us something that relates the amount of one of these phases to something that's got pH in it. Okay, so we can then start to substitute equations like this to substitute in for things like that. Which is, so we can come up with an equation that gives us the amount of boric acid and borate ion. We can just then start to plug these into there. Okay, this is what we're going to do now. So we can substitute those in, which is what I've done here, plugged in there. But the first thing I'm going to do is, rather than plug into all of them, because so basically the first term here is the total concentration of boron in the ocean. We're going to basically express that as this. Okay, total boron is equal to that, just from rearranging this equation here. Now, I'm doing this because I want to get rid of the term that has in the equation that is related to the amount of boron in the ocean, because the amount of boron in the ocean doesn't affect the speciation between the different boron species. So whack that in there, and I can kind of multiply out that term at the top here to give me this longer thing down here. And once I've done that, I can then substitute in for the other phases, which I've done here, just plugging in this and this for every boric acid and borate ion. It looks horrendous, okay? But actually, quite a lot of the things on here cancel out. Okay, so every term on here has got a boron total at the top of it, so they all will ultimately cancel out and go away. We can multiply the top and bottom by this term here, and that will get rid of basically all of these things. Well, not all of them, only the ones with H and KB. HKB, that goes away, that goes away. Yeah, so that's done there. This factorizes out. Okay. There's a little mathematical trick here in that if I divide 1 plus a fraction by 1 plus the reciprocal of that fraction, that just equals the first fraction in here, and there's the math that shows that if you want to go through that in your own time. So that simplifies out into this. And then we've got an equation that has these hydrogen ions over KBs, hydrogen ions over KBs, and we know from the previous rules of logarithms that that can be replaced with these terms here. So now, okay, so this is, I mean, if you haven't followed all of the maths up to here, doesn't matter. What's important is that we've now got an equation that relates the isotopic composition of borate iron in the ocean to the pH. Okay? And all we did, we knew the fractionation factor between the two species. We knew that the relative proportions of those species were dependent on pH. Okay? And that means that the isotope ratio of each of the species will change as the proportions change. Okay? And then we've just rearranged that equation. Okay? So we could rearrange that equation to give us pH. Okay? And that's even more hideous to rearrange, so I'm not going to go through that. But that gives us this curve of the borate ion relative to pH expressed in terms of something we can actually measure. Now, unfortunately, the borate ion doesn't get preserved in sediments. Okay? Because it's an ion in aqueous solution. The thing that gets preserved is when that boron gets incorporated into calcium carbonate. Okay, it gets incorporated into a mineral. So, fortunately for the proxy, when calcite or aragonite forms, we think, and we're pretty sure of this, that it only incorporates boron from borate ion and not boric acid. So that means that although there will be, so that's this kind of equation up here, so you get some calcium carbonate and some borate ion, and that gets incorporated into the calcium carbonate lattice in some kind of borate ion within the calcite. Now, there is going to be some isotopic fractionation between the boron inside the calcium carbonate and the boron that's in the dissolved phase in the boric ion. But we think that fractionation is quite small because when we actually measure marine carbonates, they have a value that's quite similar to what we would expect for the borate ion. But there is nonetheless this small fractionation between the two. So there's this is one of the steps that we have to go through. So if we think about what the boron has to do, so it starts out being the total boron isotopic composition of the whole ocean. Okay, and then there are some things. So the pH, the value for the equilibrium constant, okay, and the fractionation factor. So they all determine what the boron isotope composition of the borate ion is. Then that boron from the borate ion, okay, then gets incorporated into calcium carbonate, okay, which there will be some fractionation factor, and there will also be this problem of, is this really in equilibrium? Because that boron has to get through some cell, diffuse through the animal, and then be deposited as calcium carbonate. Additionally, we've got the problem that this value here of the equilibrium constant, because it's an equilibrium constant of a chemical reaction, that will be temperature dependent. Okay, as will the fractionation factor be temperature dependent. So there's some additional factors that are going to be changing our boron in our calcium carbonate other than just pH. Okay, temperature will affect these and also affect this one, and there will be some issue that are we truly at isotopic equilibrium. So this is just to demonstrate some of these effects. So these are what happens to the equilibrium constant, okay, when you do different things to the environment. So changing temperature, so that's the red line. So you can see temperature from -5 degrees to 35 degrees has quite a large effect on the equilibrium constant. Okay, changing salinity doesn't have much of an effect on the equilibrium constant. So the changing salinity is basically changing the total concentration of some of these species. Changing pressure, okay, so changing water depth also has an effect. Okay, it's because there's basically there's a small pressure effect. And what the graph on the right is showing is what is the effect of that changes in the equilibrium constant on the pKb on the final isotopic composition of the borate ion. And you can see again that temperature has a really big effect, as does pressure. So, and salinity has a very small effect. So if we're thinking about using this proxy, okay, we could maybe think, well, it doesn't matter how salty the water is, because that's a very small effect. We think, well, there's a big change if we measure carbonate at 0 meters water depth and 4,000 meter water depths. There might be a big effect in our isotope ratio that we measure just due to the pressure difference. So one thing we might want to think about doing is maybe only measuring samples that were from the same water depth. Okay, that's easy to do with planktic species because they always live in the surface ocean, so the pressure difference there is going to be very small. but maybe measuring deep sea corals might be something we have to think about. And then we're going to have to do something about this temperature, because we need to correct for that somehow, because that's a huge effect. We can't always measure things at the same temperature, or that grew at the same temperature, because that's just something we don't know. So all of these things, okay, so I mentioned if we want to measure the boron isotopes in carbonate and we want to reconstruct pH, there are all of these, this changes hugely with environmental conditions. This is temperature dependent. Is our formation of carbonate in isotopic equilibrium? Well, I don't think any of these things are working in our favour. Okay, but does it matter? So these are some basically of these empirical calibrations. So what we've got at the bottom is the pH at which things have grown, and the grey line on here is what we would predict the boron isotope composition of the borate ion to be. And you can see here that the calcite kind of closely follows that relationship, but is sometimes different. Okay, so this suggests that it is definitely that the calcite is getting its boron from the borate ion, but there is this additional fractionation between the borate ion and the calcium carbonate. Okay, for some organisms, it seems that it does quite well, and that additional fractionation that we don't really know how it works is quite small. But for other, particularly things like corals that form aragonite, it can be crazy. So what do? We do an empirical calibration. So we basically go out and we measure the borate ion composition of the thing that something is growing in, and we measure the boron isotope composition of the calcium carbonate, okay? And we just do an empirical calibration so that we can then take our measurements in the carbonate and then basically read off or convert using maths what the boron isotopic composition of the water was. That still only gets us back to the middle, okay? So we can do an empirical calibration from what we measure to the borate ion composition. So that takes into account this weird non-equilibrium fractionation that might be species specific, but it doesn't get us to pH yet, because we need to know the temperature effects mostly, and the pressure and the salinity effects on the equilibrium constant, the chemical equilibrium constant, and the fractionation factor. I guess we're also assuming that this doesn't change either, the total isotopic composition of boron in the ocean. So we're quite confident that doesn't change, because boron is quite conservative in the ocean, so it doesn't appear to vary spatially in the modern ocean, so that indicates that it's got a very long residence time. So if it does change in the past, it would change very slowly. Now, the pKb and also the fractionation factor will be dependent on temperature, so we can basically have to measure another proxy for temperature to correct for that temperature dependence on the equilibrium constant and the fractionation factor. So when we do that, okay, we can measure boron isotopes in forams, in sediment cores, and we can see how they vary through time. And because the pH of the ocean is so closely linked through the carbon cycle to the atmospheric CO2, so when you put CO2 in the atmosphere, that acidifies the ocean. So that can be picked up in boron isotopes. So what we can do here is basically see how that varies through time. Okay, and this has basically also gone through a conversion which predicts the CO2 in the atmosphere from ocean pH. And just see, I guess this is effectively another empirical calibration where we're just seeing what we predict from our boron isotopes, temperature corrected with magnesium calcium, how that compares to what we actually have in the atmosphere measured in an ice core, CO2. And that's what's expressed over here on this graph here. So CO2 measured from the atmosphere directly sampled by ice cores, and CO2 concentration in the atmosphere inferred from ocean pH, inferred from boron isotopes. And you can see that it seems to do quite well. I mean, it's not perfect, but the error bars are quite large. They all seem to overlap with the one-to-one line. So we've kind of, what we've done here is we've done a series of empirical calibrations that are species-specific, and then what we're doing here is a validation approach, where we're basically trying to reconstruct pH where at a time when we know what it was. So we can then start to apply this proxy back in time where we don't have anything to validate it against. And that's what's been done here. So this is basically going back from 0 to about 1 million years. Our ice core record ends at about 800,000 years. And you can see here we've extended the ice core record of CO2 in the atmosphere using ocean pH as a proxy for CO2 in the atmosphere, and using boron isotopes as a proxy for that pH. So this is quite useful because this shows us that actually CO2 has not been higher much than present over the last 2 million years, as opposed to the ice core records, which could only say that over the last 800,000 years. We can take the proxy back even further in time to this Paleoeocene thermal maximum, I guess now called the late Paleocene thermal maximum, which I think I brought up in the previous lecture. So this is where we saw, I guess, going forwards in time from negative to positive time. So there was this huge perturbation of the carbon cycle here, where we're adding negative or light carbon into the atmosphere and ocean. So that's probably some either large volcanism or, oh, actually it's probably, no, it's not large volcanism because it's very negative carbon. It's probably some kind of fossil fuel source of carbon, so something like methane or coal burning. So to naturally put that into the environment, that would have to be something like a gas hydrate release from high latitudes. So that puts a lot of carbon into the atmosphere. You can see the magnesium-calcium ratio here is indicating warming at this time. And we have a boron isotope record that gives us lighter boron isotopes, which indicates that we're getting more acidic conditions during this time. So that kind of fits with what we know about the carbon cycle. If you put lots of CO2 into the atmosphere, then you expect the pH of the ocean to go down. Okay, so to summarize this lecture, so the isotopic equilibrium is often not achieved at all. Okay, so it's although it's the underlying mechanism for why we think there is a temperature dependence on isotope fractionation, we actually don't get close to that theoretical kind of value for the fractionation between two phases. Although if we do an empirical calibration, okay, so if we just go out and measure some things that grew at different temperatures, we get the same kind of relationship that we would expect from theory, but it's not, we don't get the exact values for that relationship. So we have to use these basically calibrations to use paleo temperature proxies. In the case of boron, this pH dependency arises because of this large fractionation between two phases and the basically pH dependency on how much of each phase we have, which can be used as a proxy because only one of the two phases, or one of the two species, the borate ion, gets incorporated into calcium carbonate. Okay, and because of that, that means that the pH, as that changes, that will change the boron isotope composition of the calcium carbonate that's produced, but that will in turn also be dependent on this kind of non-equilibrium fractionation between the borate ion and the boron in the calcium carbonate, which we need to correct for using an empirical calibration. And we also need to take into account the other things that are affecting the isotopes. So that's mostly temperature, but can be pressure as well. Okay? Right, so that is the lecture part of the thing today. So what we're going to do now is we're going to do a kind of a workshop on stable isotopes in exam questions. So what I've done previously is I've handed out these like past exam questions, which are also posted on Learn, and got you to work together in groups to come up with kind of outline answers for those. Now I'm going to do it in a slightly different way this time, and we might revert to this if it all goes horribly wrong. So what I've got instead are these, which are not exam questions. They are very blank. They're just pieces of paper with very broad topics on them to do with some of the stuff we've been doing with isotope fractionation. And what I want you to do is to work in groups of maybe 4 or so, or 3 to 5, 4. Now that doesn't really matter. And I'm going to give you one or some of these. And what I want you to do is write an exam question, okay, for each of the subject areas that you think kind of covers the material that has been taught in that area, okay? And it asks a question in such a way that, so the simplest, okay, question would just be to add the word why in front of, so why kinetic isotope fractionation, okay? So try and think up questions that basically, I guess, dig into a little bit more detail, or ask for examples of, or ask into specific parts of the theory that we've gone through. Okay, and then I'll come round and we'll discuss those as we go around. Okay, so we've had an hour, and I think some people were also breaking out to either tactical chunder or go to the loo, whatever you're doing. So I guess we have a bit of a break, but I guess it's quite going to be informal, this thing. So form groups, and then I'll come around with some of these things. And we've also got Rachel, who's going to come and help and chat and whatnot. So Rachel's doing her PhD using isotopes to trace sources of CO2 for carbon capture and storage. So you can talk to her about that and how she loves isotopes. That'd be super awesome. Right. All right. Yeah, so there are. Yeah. Yes. Well, let's see.